Hello everyone! Gasp, how embarrassing. That's from my IGCSE physics lesson earlier. Oh, I feel like a teacher having stuff from other lessons on the board. Hello, this is not IGCSE physics. This is all ages home ed. This entire term we are looking at learning scientifically and thinking scientifically, and this lesson is on models. I want you to imagine that you want to learn the difference between male sparrows and female sparrows. I mean, who doesn't, right? House sparrows. What's the difference in appearance between a female house sparrow and a male house sparrow? So I have some pictures here, like pairs of pictures, and I want you to just tell me, explain, write it down if you like, or just say out loud, which photo or picture you would use, and which photo or picture you wouldn't use, and why, okay? Harrison's saying butter tub. There's no such thing as a butter tub. Come on, who doesn't know what a margarine tub is? Butter doesn't come in a... I suppose some butter comes in a tub. Do you know what? I'm going to have to stop thinking about this. Right. You want to know the difference between male and female house sparrows. Excuse me. Explain which pair of images you'd use and why you wouldn't use the others. So A is a pair of photos of house sparrows. B is a colour illustration of the sparrows. And C is a black and white illustration of the sparrows. Which pair of photos are you going to use to learn the difference between male and female sparrows? Yeah, Gregor, there's two wormies here. Theatre of Science mascot wormies are always skulking in the background. Well spotted. Just going to get some water while you decide which pair of sparrows is the most useful. This lesson's pleased me greatly because I had to do a little bit of research on sparrows for this starter bit, so I get to talk about sparrows as well. That's better. All right, what you get? Everyone's saying A. Yeah, everyone yesterday was saying A as well. I'm a bit disappointed that everyone's saying A, to be perfectly honest. Ah, yes. See, Freya is saying there's no colour in the third one. Yeah, Roman. Roman's saying you wouldn't use C because it looks like a picture from the olden days. What's wrong with the olden days? Yes, someone is saying that there isn't very much colour. What's Olivia saying? Someone's liked what Olivia's saying, so it must be good. Let's have a look. A would be best because the colour's a true tone. Ah, good point. It's a bit more. It's a bit more in detail, and you can easily see which is male and which is female. Yeah, all right, fair enough. Okay, so. Oh no, yeah, I did think this is the only lesson we've ever done where you have to have a colour printer, but you can look at the screen. Thank you, Leon. Leon is an artist who lives locally, but Leon is saying that he loves a bit of B. So take note, everyone. Mikey is saying A and B. Yeah, right, that's totally fair. Okay, I'm not going to talk about it until a few minutes later. I'm going to get you to do another thing, okay? So come back up here with me. So the second thing I'd like you to do, I might do it better today because I've had a practice. I'd like you to get a pen and paper, right? And hold the pen in the hand that you used to write and put the other hand away somewhere. I'm going to stick it between my knees because I'm a bit chilly. So hold a pen in the hand that you write with and put your other hand somewhere where it can't be seen. And what I want you to do is, with this pen, I'd like you to draw your hand that you can't see. Okay? Not allowed to look at it. Don't look at your hand. Just draw a picture in as much detail as you can of your hand that you can't see. Yeah, wow. I hadn't done this until I made you do it. I was staggered at what an appalling job. Leon, are you doing this? I'd be interested to know that if you're like a proper artist, if you're a pro, how good a job you do. Right, we're going to spend too long on this because this is just making a point, okay? I don't know why I've drawn it so tiny. Right, you've got 5 seconds to finish off the picture of your hand. 4. Oh no, wait, Anna. 3. I just realised I haven't even put fingernails on. 2. What else is there? And 1. Right, stop what you're doing. Drop your pen. Have you drawn a picture of your hand? So this is the hand that I drew. Maybe yours is better. Maybe it's worse. I don't know. So I have done this already. So I knew, because I've been studying my hand, that there are some sort of tendons in the back of my hand, so I've drawn these lines. What I'd like to do is, you've got 10 seconds now to study the hand, get the hand out from wherever it was hiding, have a good look at it, study it carefully. You've got 10 seconds, and then I want you to add as much detail as you can to your picture of your hand, all right? So give it a good study, move it around, see how it works. Wow, I'm really seeing things I didn't see yesterday. 5 seconds, just keep staring at your hand, recall as much detail as you can. 5, 4, 3, 2, 1. All right, put it away and add as much detail as you can to your hand. That seemed longer than 5 seconds. Oh yeah, my seconds are never actual seconds. It's just what, like teacher seconds, whatever I feel at the time. Right, come on, add some more detail. I should have said to do it in a different colour really. Yeah, so I've seen lots of things actually that I didn't know before. Yeah. Did I say 10 seconds? Right, now you've got 5. 5 seconds to finish off. Add all those details that you just noticed. You ready? 4, 3, 2, and 1. And finish. Right, how did you get on? Send me a picture of your hand if you like. I noticed that I've got lots of, what do you call them, moles? Like freckles on the back of my hand and some hairs, and that my thumbnail is all a bit messed up, and that my different knuckles, it doesn't matter. This isn't a lesson about my hand. What we're talking about is models. What a model is, a scientific model is just anything that helps you to understand how the world works, really. So when we say models, we're used to thinking about, you know, things that we can hold in our hands. And that would be a scientific model, like a globe. Man, I wish I'd remembered to bring it. A globe is an excellent model of the Earth because it explains a bit about how the Earth works, right? If you've got a globe that spins around, then that helps you to understand how Earth spins around. You might even have one of those posh globes that's got little raised bits on it to show you like where the mountains are. So a globe is a good scientific model of Earth because it helps us to understand how Earth works. But obviously it's not actually Earth. I mean, because you can't get the Earth and study it. So we use a model instead. But a model doesn't have to be something you can hold. So a picture is also a model because it's like a representation of something that helps you understand how it works. So probably drawing a picture of your hand has helped you to understand how your hand works, right? Like I hadn't noticed that I've got loads of hairs on the back of my hand. So that's something that I learned through a model. You've probably seen your hand a lot in your life and maybe never noticed things that you noticed today. So you were all saying that you would use the photographs of the birds, but it's not always the most useful thing to use the actual thing to learn about. Sometimes it's better to use a model. Like, I'm going to show you the RSPB's website, right? The Royal Society for the Protection of Birds. On their website, and they're like the bird people. If you want to know the difference between different sparrows, or any kind of bird, they show you photos, yeah? So look, there's a male, there's a little baby one, a juvenile, and there's a female. I'm assuming that the reason that they do that is often models are more useful than the real thing because they've got less detail in them. And sometimes it's good to have less detail. So for example, a map is a very good example of a model of something where you've stripped away all the detail and just left the useful thing. So for example, we're standing here and you say to me, can you tell me how to get to the shop? So I would draw you a map like this that said, oh yeah, you just go like straight down this street, you get to a crossroads, you go left, and the shop is there. If I went, oh, and there's a beautiful statue of like a cat on this corner, and oh, and there's a tree here, and oh, there's 6 more shops here, you'd be like, what are you doing? Stop, shush, this is just confusing the issue. You don't want a lot of detail. You want to strip away the detail and focus on what's important. So, oh yeah, so I said I'd tell you a little bit about sparrows. I mean, they are excellent photos, actually, that I've chosen. So you might well use those photos. But some people would argue that the illustrations make it easier to see the difference. Because one of the main differences between a male sparrow and a female sparrow is this like creamy coloured stripe here, which is called the supercilium. I just learned that word. This is the supercilium. So on a female sparrow, it's a house sparrow. It's kind of creamy coloured and it's got a brown bottom bit. So, I mean, you can see that on there, but you might not have noticed it as easily because there's a lot of other detail going on. Certainly, I think if you look at the wings, the patterning on the wings, it's much easier to see here that they've both got this white bit. Whereas here, there's so much detail, it's harder to see. So the black and white one, well done if you said that that didn't have as much detail in it, did it? It was sort of too little detail because it's in black and white, so you can't see the colours. But some people would argue that the pictures make it easier. So I said to bring, throwing people into confusion, I said to bring some kind of pot or tub, a butter tub if you like, or a margarine tub or a yoghurt pot with a hole in the sides. So I've got a yoghurt pot here with a hole like just slightly smaller than a 5p, about halfway up. It really doesn't matter what kind of tub it is. It could be one, like you could have chopped the top off one of those card juice boxes or milk box or something. But yeah, just put a small hole in it anywhere. And just get a big jug of water. I'm using a big baking tray so that you can see it, but a washing up bowl would be fine as well. We are going to talk a little bit about global warming. How Earth is heating up, because when you talk about scientific models, this is one of the most important things that humans are modelling today. So how does Earth heat up? Well, let's really simplify it, okay? Here's Earth. Beautiful and green. Here's the sun, yellow, true colour of the sun. What happens is, energy comes from the sun. Can't really see that, can you? So energy comes from the sun, okay? And is absorbed by the Earth, taken in by the Earth. Let's label the energy. And what also happens is that the Earth gives off energy. So the Earth absorbs energy from the sun. Let's do the arrows to show the direction. And it gives off energy as well. It radiates energy, okay? It absorbs energy and it emits it back into the atmosphere. And this is how Earth keeps a steady temperature, yeah? And actually, the more energy it absorbs, the more energy it emits, all right? So generally speaking, the Earth has always got a fairly constant temperature. Let's do a model to try and understand this better, okay? We're going to get a yogurt pot with a hole in the side. And we're going to say that the water that goes into the yogurt pot, this is water going in, shush, it is. The water going in is the energy from the sun. And we'll say that the water that comes out of the hole is the energy like emitted. And we'll say that the water level in the yogurt pot is Earth's average temperature. So the water level is Earth's temp, okay? So we've got a yogurt pot. The level of the water is Earth's average temperature. The water that goes into the yogurt pot is going to be like energy shining onto the Earth, and the water that comes out of the yogurt pot is going to be like energy leaving the Earth, okay? So it's a model. It's a model for global warming. Right. Water is a precious commodity, so I'm using this old tea topped up with old washing up water, which is why my water looks so weird. Don't be worried for my health. But what's happening first of all? Well, there's no water going into the pot. So if there was no sun shining on the Earth, if no energy was going into the Earth, what would the temperature of the Earth be? Well, it would be very low. So this is quite a good model already, isn't it? Look, we've just got a cold, dead Earth that has zero temperature because there's no energy being absorbed into it. So let's pretend that we've switched the sun on. And look, the temperature of Earth is rising. And as the temperature of Earth rises, look what happens. The Earth starts emitting energy, and this is right. So can you get it, I've got a posh teapot, you might be using a jug or a glass. Can you get it so that the energy in equals the energy out? I think I've managed it, haven't I? How will we know? We'll know because the temperature of Earth, the level of the water, won't be changing, yeah? So this is how Earth's temperature has been for about 1 million years. Roughly speaking, the energy going into the Earth has equaled the energy being emitted by the Earth. And so the temperature of the Earth has remained constant. Now, there have been fluctuations, you know, like if my hand wobbles, then some more water goes in. But if I do that, then hopefully more water starts coming out as well. So eventually the water level changes, the temperature of Earth goes up, but you get back to a steady state again. Let's really trickle it this time. Here we go. So for some reason now there's less energy going into the Earth, being absorbed by the Earth. And you can see that the temperature of the Earth is going down. The water level of the yogurt pot is going down. It's going to go down and down and down and down. But hopefully, yeah, at some point it'll balance out again. So now the amount of water leaving the yogurt pot is the same as the amount of water going in. So we've got a cooler temperature, but it's back to being a steady state. Is that okay? So this is what's happening with the Earth. except it's not at the moment because humans are doing activities which is producing a lot of greenhouse gases, carbon dioxide, which means that more energy is effectively being absorbed by the Earth than is being given off. So at the moment we have a situation where the water level is rising like this. It's massively simplified, enormously simplified, because there's loads of different factors that affect the temperature of the Earth. Like the amount of ice on Earth affects it, because ice reflects the sun's energy. So the more ice on Earth, the more sunlight bounces off it effectively and back into the atmosphere. So when ice melts, that means Earth absorbs more. The oceans absorb an awful lot of energy. Clouds do, the atmosphere. So if we were going to do a more detailed model, we'd need to take all those different things into account. Luckily, we don't have to, because we have computers. So computers are now used to model global warming. Because we can just put all the different numbers in, all the different data, change any little thing that we like, and the computer gives us the right answer. So I looked up on the internet, because I'd never really thought about how did we model global warming before computers were invented. And it turns out we didn't. Like, no one was really bothered about it, no one had thought about it. But the first person to model global warming on a computer is quite a cool story, so I thought I'd tell you it. It's the 60s! And Suyakuro Manabe is senior researcher, meteorologist at America's National Oceanic and Atmospheric Administration. You might have heard of them. The NOAA website is excellent. A lot of beautiful pictures of fish. So he's really rocking out the 60s. He's very excited because his department gets a computer. Ooh! Now it's the 60s. So the computer is slow. Like, this is the oldest computer picture I could find, but it surely looked a lot older than this. The computer is so slow, it takes hundreds of hours to run very simple simulations. I mean, yes, I'm sure it's very impressive at the time. Everyone was very excited. But it's slow. You need to keep things simple for this computer. But that is what Dr. Manabe does. He decides to run a simple model for climate change on it. So He just looks at the relationship between the atmosphere and the ocean and the clouds. And he decides to run a simulation changing the amount of carbon dioxide in the atmosphere. The results shock him. It's amazing. What happens? Well, if you take all the carbon dioxide out of Earth's atmosphere, the computer simulation would show that this reduces Earth's temperature by 30 degrees. Raising the levels of carbon dioxide increase Earth's temperature. This is obviously not a surprise to us now, but it's not a surprise now partly because of the work that Dr. Manabe did in the 60s. This was a mega surprise. No one really paid any attention to this for years, because temperatures in the 50s and 60s, you know, we talked about like natural fluctuations. Temperatures at the time had actually fallen slightly, so no one is worried or thinking about climate change. But in 2021, just last year, Dr. Manabe received the Nobel Prize in Physics because the study had made such an impact on the world. People looked back and realised it was one of the most fundamental studies that had been done on like the planet's future. So very well done, Dr. Manabe. I did not hear about it last year, but I'm very pleased that I heard about it now. Models change over time. If you do like IGCSE physics, this is one of the things that they stress. It's very important that you know models change over time. So I thought I'd tell you a little bit about how models have changed over time. Right, you probably know a bit about atoms, okay? You probably know, if you don't know, then we'll explain it briefly now. An atom is positive particles called protons. There's neutrons in there as well that don't have any charge. We'll kind of ignore those. Positive particles called protons with tiny little electrons whizzing around the outside. So negative things repel negative things. So two negative things push away from each other. A negative and a positive thing come towards each other, attract each other. It's like magnets, okay? Opposites attract, things that are the same push away from each other. So an atom is, positive charge in the middle, loads of empty space, and then teeny tiny little electrons whizzing around it. But we didn't know this for ages. Like, you can't see atoms. How are you going to know that? For hundreds of years, what people thought an atom was, the model of an atom at the time, was the deliciously called plum pudding model. This is the plum pudding model of an atom, developed by J.J. Thomson. So all through the 1800s and the start of the 1900s, what people thought an atom looked like was a kind of ball of positivity with delicious little tiny kind of currents of negativity dotted through it, all right? And this was the model. If you were learning about atoms at school, this is the model that they used. That's an atom is like this. It doesn't look exactly like this, and this is what it's like. And then someone called Rutherford in the early 1900s did an incredibly famous experiment where he got, let's draw it in red because it's the same. He got something called alpha particles. An alpha particle is basically just a very big positively charged particle. He got a sheet of gold atoms. So remember, these are atoms, so just like a kind of big layer of gold atoms. And he fired alpha particles at the sheet of gold atoms. Now, what was he expecting to happen? Well, we've got a very kind of weak positive charge all the way through this. So what Rutherford was expecting was that the huge positive alpha particle would pretty much bash straight through and get to his sensor, which was set up at the other side. So what he thought would happen was this. And maybe because there's a bit of positivity here, like maybe some of the alpha particles would be deflected a little bit. Like they'd interact with some of the positivity and they'd get a bit bent. This is what he thought would happen. And this is mainly what happened. Mainly what happened is that the particles just bashed straight through to the other side. But occasionally, just very occasionally, this would happen. The alpha particle would bounce off the sheet of gold. Rutherford said it was as if you'd fired a cannonball at a piece of tissue paper and the cannonball had bounced back. Just unbelievable. Like, how weird. How would you explain that? Cannonballs bouncing off tissue paper. Well, the only way to explain it is you got to go back to your tissue paper and rethink it. So Rutherford is the person who, after this experiment, realised that the plum pudding model was incorrect. And what is actually happening is that an atom is mainly empty space. So you have positivity right in the middle, which is what occasionally the alpha particles were bouncing off. But most of the atom is empty space, and the electrons are whizzing very far around the outside. So that's how models change over time, based on experiment. The other thing to say is that this isn't actually a very good model of an atom at all. That's the dangerous thing about models, is that sometimes they're simplified because it helps us to understand it, but it's easy to forget that it's just a model. So, for example, like some of you will be very familiar with this as a model for an atom. You don't know that actually the electrons aren't orbiting the protons like this at all. They're just whizzing around in a cloud. The electrons, if you were going to do a better model, you would draw it like this, just a fuzzy cloud of electrons. But obviously, if I'm teaching you about how many electrons are going around a certain amount of protons or whatever, this isn't a very useful drawing. The other thing is, I've just said that it's mainly empty space. It's really, really mainly empty space. Like, the electrons are so much smaller than the protons that it's unbelievable. And there's so much space here. But obviously, I can't show that either. Like, it would be much more realistic to say, oh, the protons are like this, and the electrons are like this. But that's not a very good way to learn about atoms either. So this is the kind of the dangerous side of models, is that they can make you feel too comfortable, like you understand it, when actually you don't understand it. Okay, usually at the end of the lesson, do the plus bounce off each other or destroy each other? Oh, what a great question. Yeah, they don't actually touch. It would be like two very strong magnets that were pushing against each other. They kind of get a certain distance and then they repel. Very good question, Roman. Yeah, so they don't actually touch each other. It's like their electrostatic fields. Don't let them get any closer. Just like really strong magnets, you can't push them together. Yeah, usually at the end of these lessons, we do some GCSE past paper questions. There aren't really any past paper questions that were suitable for scientific modelling. So what I've done is I've set you like a little puzzle instead. This is a true story. This was sent to me by somebody, so I'm going to pass it on to you and see if you can work it out, right? Your friend sends you a secret report by NASA discussing an aircraft they've designed that can fly over a flat, non-rotating Earth, okay? I'll show you the document, it's online. They've designed an aircraft to fly over a flat Earth that is not rotating. And your friend says that this is proof, this secret document is proof that the Earth is flat, and NASA knows it's flat, and they're trying to cover it up. It's a true document. This is literally on NASA's website. Here we go. So August 1988. derivation and definition of a linear aircraft model. You won't understand it all, that's absolutely fine. I just wanted to show you that it's a proper NASA document. And if you go down to the introduction, I've taken a screenshot, I'll show you, but I thought I'd just prove to you that this is real. If you go to the introduction, they're saying, this report details the development of a linear model of a rigid aircraft of constant mass, so it just means like its weight isn't changing, if you like, flying over a flat, non-rotating Earth. What do you say to your friend? Okay, your friend sends you this report. This report details the development of the linear model of a rigid aircraft of constant mass. It doesn't matter if you don't understand all that, but look, flying over a flat, non-rotating Earth. Your friend says this is proof that Earth is flat, and NASA and other organisations are trying to hide the truth. How do you respond? Do you agree or do you disagree? So I'd like you to write or say, I disagree / agree with my friend and why. Okay, so Brian says disagree because the Earth is round. Totally fair enough. Yeah, Gregor's the same. Just disagree because round. Yeah, but how do you explain this? How would you explain NASA talking about a flat, non-rotating Earth then? Maybe I should have phrased the question differently. Why has NASA written this? Maybe that should be my question. It's not enough proof. Okay, no, but is it some proof then? That should have been my question. Next time I teach this, I'm going to ask, why have NASA written this? Can you explain why this thing is on the internet? Why did NASA design a plane to fly over a flat, non-rotating Earth? Yeah, Freya's just like, well, the Earth's not flat. Disagree is the craft. Oh, the craft could be used for something else. Okay. Interesting. Harrison's suggesting that maybe there are two Earths. Don't make it even more confusing. Don't feed the conspiracy theorists, Harrison. Tomorrow there'll be a website like, there are two Earths. It's not a fake, it's totally real. Why are NASA designing aircraft for flat Earth? Well, it's the same as this map, isn't it, right? You remember the map? You want to know how to get to the shops. So I draw you this map. Here's the shop. Is this map proof that there are no trees in this town? Is this map proof that there are no trees in this town? No, of course it's not proof that there are no trees in this town. So why doesn't this map have any trees on it? Why? Do you remember why? Why didn't I put any trees on this map? Because they were unnecessary, weren't they? It was just extra detail that I didn't need. It would have taken me more time and energy to draw trees on this map, and they didn't help me achieve what I was trying to achieve. It's exactly the same with this. As I tried to explain to the person, it wasn't a friend. It was someone who wrote to me very angrily via my Facebook page because I've been teaching people about Earth and how it was like round, and they were saying, no, it's not. And they showed me this as proof, and I tried to explain and say, look, this is just NASA were building an aircraft, but to make their calculations simpler, they've used a model of the Earth being flat and not turning, because they didn't have to put into the computer, into the aircraft design, the Earth is round and it's spinning, because that would have taken more time and more energy and probably more money. And it didn't really affect the design of the aircraft. They were simplifying. So to make things simple, they were imagining that the Earth is flat and not turning. And that's why. For a start, it's not a secret document. It's just from the 80s, so obviously nobody's reading it now. Models, they can be used for evil. Okay, thank you so much. They didn't understand. Some people just want to believe that the Earth is flat because problems with authority. It's not really a science issue. Thank you so much for coming. That is the end of the lesson. If you do not understand how I'm doing this for a job, it's an amazing business model. Business model? Yeah. If you go to my Facebook homepage and you click sign up, children, don't you do it. But if you're an adult and you're using me and you're enjoying this, then you can pay me £5 or £6 a month by clicking sign up. It takes you to this website called Coffee, where you pay me £5 a month for the lessons and I send you nice things. So very grateful am I that it's my job. So if you sign up now, I will send you Theatre of Science magazine. Thanks, Betty. I love writing it. It's like I'm writing you guys a letter. So this one's on seeds. So I've got you a packet of mystery seeds that you can try and grow. There's a quiz. Which seed are you? There's just a lot of information in it, because I always feel like science magazines for kids are a bit like, cool fact about this. No, I'm going to give you a whole article about this. There's a comic that I wrote and my husband illustrated about pollination, lots of ideas for activities. Yeah, I'm super proud of Theatre Science magazine. This is the bumper issue, so now is a good time to sign up. Origami Lotus, that took husband ages. Okay, right. Thank you so much for coming, you guys. And thank you very much to everyone who's supporting my lessons and making this my actual job. Bye bye, bye Freya, bye everyone, see you soon. I am an adult in 2 and a bit years. What? No, wow. You're an adult in 2 and a bit years. Blimey. Oh, I am 40 next week. So I'm like adult squared next week. So the next week's lesson might be pre-recorded, but I haven't quite decided. In fact, I think it probably will be pre-recorded because I've been wanting to do a lesson for a while that kind of has to be pre-recorded. So I might end up kind of watching it along with you in the comments. I don't know. I'll tell you more later. Bye, Percy and Trish. Thank you so much for coming. Thank you for calling the phrase science fiction. Oh, look, Juliet is still here and they're going to sign up. Amazing. Thank you so much. All right, well, I'll go and let you do that. Bye. Thanks, everyone. See you next week.